Okay, so if we look at your homework, actually, I think I have it. I don't know what's going on. I think it's laggy because I'm got Zoom and I've got OneNote, which always causes problems, and I'm trying to record, so I think that's why it's so laggy. Okay, so this problem, you are going to have to, for your circuit, write the excitation equations, write the transition or next state equations, write the output equations, draw the state output table with flip-flop outputs as states, draw the state diagram including the outputs, and use transition expressions. So we are going to do all of those things, these same steps, for the smaller circuit that I have there, and in addition, we're going to write the Verilog that goes with it. So that'll take care of both your homework and your lab. Okay. So, all right. So the first thing that we need to know is that we've got D flip-flops, and so you need to know the characteristic equations for a D flip-flop. So for a D flip-flop, the characteristic equation is very easy. So Q star just equals D for a D flip-flop. So that's easy. Um, you will need to know for your homework the characteristic equations for other kinds of flip-flops, and if we get to them, we'll use these, but just so that you'll have them handy, I'll go ahead and write them down. So for an SR flip-flop, actually, I don't think you have an SR in yours, do you? Well, we'll write it anyway. So for SR, Q star equals S plus R bar Q. And you also want to check and make sure that SR equals 0. So an SR is a little different because the input of 1, 1 can cause problems. And so if SR always equals 0, then you're safe with an SR. Okay, and then for a JK, the characteristic equation is Q star equals J Q bar plus K bar Q. And for a T flip-flop, Q star equals Q exclusive OR T. And in case you've forgotten what the exclusive OR does, another way you can write the exclusive OR would be Q T bar plus Q bar T. That's the same as exclusive OR. And then we have the D already up here, so this is for the D flip-flop. So you'll need those for coming up with your next state expressions. So these are important for your next state expressions. So for your excitation equations, this is where you're actually figuring out your values for D or S or J or T or K or R. those are your excitation equations. So those are the things going into the flip-flop. And so for ours, if we look at this top one, so this, I'll call that one D1. So D1 equals, we have an OR gate, and this OR gate has coming into it both, so this one is Q2 and this one is Q1. So the OR gate has coming into it Q2 as well as Q1. So that's our OR gate. So our OR gate, so this is actually D2. I wrote D1, so this is D2. So D2, the OR gate has Q1 or Q2, and then that is ANDed with our input. Our input is W. So that's D2. That's our excitation equation for D2. And then D1, if we look at D1, D1 is the AND, so it's this AND gate right here. It's the AND of Q2 bar and Q1 bar and W. So those are the excitation equations. Now, our next state equations, since these are D flip-flops, they're easy. So our characteristic equation for a D flip-flop is that Q star just equals D. So Q2 star equals Q1 plus Q2 times W, and Q1 star equals Q2 bar, Q1 bar, W. Now, on your problem, these are going to be, all of these are going to be more complicated, and you'll need to simplify them using Carnot maps. And again, if we have time, we'll do those. We'll do an example of that. But so you will want to have them simplified. You won't want to have them out, like if you look at your homework problem. Yeah, here's your circuit. So you can see just, your raw equations are going to be pretty big with all of those inputs. Okay, so now we want to come up with the state table. And on your state table, you will have your present state, and we have two flip-flops, so that's Q1 and Q2. For your lab and for your homework, you'll have 3. So present state Q1, Q2. And then you'll have your next state, and your next state will depend on your inputs. Now, we just have one input for this problem, and that's W. So we'd have W equals 0 and W equals 1. If you have 2 inputs, then you'd have 4 possibilities, because you would have, let's say you had WX. You would have WX is 0, 0, WX is 0, 1, WX is 1, 0, and WX is 1, 1. So we just have just the 2. And not only that, this was a Moore machine. So our Moore machine, it just has an output. The output doesn't depend on W equals 0 or W equals 1. If we had a Mealy machine, then we would have to have 2 columns here, W equals 0 and W equals 1. Or 4 columns if we had 2 inputs. So we have two flip-flops, and so that means we have 4 possible states. 0, 0, 0, 1, 1, 0, and 1, 1. So we'll put those here. If you had 3 flip-flops, you would have 8 possible states. And I realize I skipped something. I'm going to go back and do it. I did not say what our output was. So our output, Z, is Q2. So our equation's real simple. Z just equals Q2. So that's our output equation.
So just whatever the output is,
because when I look at it, that's what's going into it. Yeah. If you remember earlier when I was giving the example of the Mealy machine, I drew an AND gate, and that one would have been Q2 and W would have been your output equation. Okay. So output Z. And then, this gives, what I want to put here, I'm going to put Q1 star and Q2 star and Q1 star and Q2 star, because when I write these, I'm going to put both numbers in there, because I'm going to identify the state based on both of the bits that are in there. Okay, so now when I look at these next state equations, at this point, it's very helpful for me to divide them up based on my input and have different expressions for my different values of my inputs. So I just have one input, which is W. So if W equals 0, then Q2 star equals 0 because it's ANDed to W, and anything ANDed to 0 is 0. And Q1 star also equals 0. And if W equals 1, anything ANDed to 1 is just itself. So if W equals 1, Q2 star equals Q1 or Q2. And Q1 star equals not Q2 and not Q1. Okay, now when I do my next state, I do 1 Q at a time. So I'm going to start with Q1. And, well, Q1 star and Q2 star, well, they're really, this one is, obvious when W is 0, they're both 0, so I don't have to do any work. These are all just 0, 0. Okay, but when I go to W1, I have to do, W equals 1, I have to do a little more work. So I'll start with Q1 right here. And Q1 star is Q2 naught ANDed with Q1 naught. And just because I'm really bad at making careless mistakes, I'm just going to write those here. So these are just the complements. That's 1, 1, 0, 0. and 1 0 1 0. This is just to help me. I wouldn't actually put this on the thing that I'm turning in. It's just kind of notes. And so I'm ANDing these two together. So that's what Q1 star is. And so notice that the bottom three all have zeros. And if anything is a zero when you're ANDing it, you get a zero. So these are all zeros. So the bottom three are zeros and the top one is a 1. So it's 1 0 0 0. And then Q2 star is Q1 or Q2. And remember, with an or, if either one of them is a 1, then your answer is a 1. And so that would give us a 1 for the top three and a 0 for the bottom one. Now our output Z, remember Z was just equal to Q2. So I'll look at my Q2 column right here. And Z is going to be equal to Q2. So that's 0 1 0 1. Okay. Do I have any questions from anybody here or anybody on Zoom?
Why is, could you just go to Q2 star again?
Yep.
Like the first one, like, why is it 1?
Why is that 1? Because it's an OR and not an exclusive OR. So Q2 star equaled Q1 or Q2, and that's not a 1, that's a 0. And this one is a 1. I was looking at the complements. Was that your question?
Yeah, that's why I was confused.
Yes, thank you. Thank you. And I even looked over to check my notes to see, oh yeah, that's the same. No, it wasn't the same. Okay, so any questions from Zoom?
Nope.
Okay. All right, so the next thing that you usually do, you don't have to do this, but I find it a lot easier, is that you give a label to each state so that we don't refer to them by their binary numbers. And so I'll call this one A, B, C, D, and there's no right or wrong way to do it. That's just, I usually just do alphabetical, A, B, C, D. And then you can redraw your table with the states. So I have present state, and then I have next state, and I have next state for W equals 0 and W equals 1, and I have output, and I have my 4 states, A, B, C, D. And then for my states inside the table, I just look and see how it's defined. So here I have 0 0. So 0 0, that corresponds to state A. State A is 0 0. That's how I defined it. And so when W equals 0, these are all state A. And then 1 0, that's state C. And then 0 1 is state B. And then my output is going to be the same. That's still just 0 1 0 1. Okay, so the last thing that we have to do is, so this is our state table, and the last thing we have to do is our state diagram. So for our state diagram, we represent each of our states with a circle, and once you've drawn it, you can see, oh, well, this would be neater if I arrange these in a different sort of way, but you don't really know until you've drawn it. So this is A, B, C, D, and it might be helpful to write down their definitions. It might not. Now, this is a Moore machine. That means the output depends only on the state. That means we're going to write our output on our states themselves. We're going to put our output right here on the state. If it was a Mealy machine, we would put the output on the transition arrow that we draw as we're going from one state to the next. So here we know in state A, Z is 0. In state B, Z is 1. In state C, Z is 0. And in state D, Z is 1. Okay, so now we have to write our transitions. And the way you do that is for each state, there will be two different possibilities corresponding to W equals 0 or W equals 1. Probably. I mean, it could be that there's only one possibility, that it always does the same thing, in which case we'd only have one arrow. When you have two different inputs, you have 4 possibilities, possibly, but you might be able to condense them down to 2, just depending. And this is where he said use transition expressions, and I'll show you what we mean by that. So when, we'll start with A. When W is 0, we go back to A. And W being 0, that corresponds to W bar. That's our transition expression. When W is 1, our next state is C, so we go here, and W equaling 1, that is just W. So now let's go to state B. When W is 0, we'll go to state A. And when W is 1, we go back to state B. And now I can go to state C. When W is 0, I go to state A. And when W is 1, I go to state B. And finally, I go to state D. And when W is 0, I go to state A. What? Oh, supposed to write it like W bar. And when W is 1, I go to state B. Okay, so what we just did shows all of the things that you have to do for your homework problem, but your homework problem is a lot more complicated, and if we have time, we'll do a more complicated one. I am going to stop right now and save this, and then we're going to do the Verilog that goes along with this problem. So give me just a second.